For question 1b, it asks us to plot a corresponding acceleration time graph with the appropriate values, variables, and units. It asks us how we did this. Well, if we go back to our mnemonic that says xva, and we go in this direction, we need to calculate out the slope. Well, if I calculate out the slope, I've got to calculate out the rise versus the run. So the slope we know is the rise divided by the run. It looks like the rise is 8 meters per second and the run is 4 seconds, so I get a slope of 2 meters per second squared. And notice the slope is constant, and it's always constant from the 0 to 4 second mark. So when I graph out the acceleration, I'm graphing it out in meters per second squared over 0, 1, 2, oops, that's a mistake there. Use an eraser here. And we're going to, it's a pen here, so at 2 meters per second squared, it is a constant at that value from 0, 1, 2, 3, 4 seconds. So we've got an acceleration of 2 meters per second squared from 0 to 4 seconds because the slope of my velocity time graph tells me that I've got a constant 2 meter per second squared acceleration. 1C asks you to look at the acceleration time graph and to say whether the motion is constant velocity, constant acceleration, or both. Well, it's constant acceleration, and here's why. On our acceleration time graph, we decided that it was a constant value. So this flat horizontal line on the acceleration time graph tells us we've got indeed constant acceleration. On the velocity time graph, we had this sort of shape. And because the slope tells us that we've got a constant slope, because it's a straight line, we therefore must have a constant acceleration. And the reason for that is that the slope of an acceleration time graph, the slope of a velocity time graph is the acceleration. So if this is a constant slope, we must have a constant acceleration. 1E says from just looking at the position time graph, is the motion constant velocity, constant acceleration, or both? Okay, and again, since it's the same particle, it's going to be constant acceleration for the acceleration time graph, the velocity time graph, and the position time graph, again, because it's the same particle. Now, if I look at that position time graph that I plotted out earlier, I got a shape that looked like that, an upward opening parabola, and a parabolic shape, therefore, tells us that we've got constant acceleration when it comes to the position time graph. Finally, on the last page here, 1F asks us to observe the velocity time graph and ask what the slope is and what does it physically represent. The slope, as we calculated out before, is the rise divided by the run. So the slope is equal to 2 meters per second squared, and that physically represents the acceleration. One G asks, what's the vertical intercept? And the vertical intercept's right there, so where the line crosses the vertical axis. And that value is -4 meters per second. Okay, that's a vertical intercept, and that represents the initial velocity. 1H asks us to write a y equals mx plus b equation for the velocity time graph. Well, instead of y in the vertical, we're now using v. So I'm going to substitute v in this equation. For m, I've got a slope that we said earlier was 2 meters per second squared. My horizontal axis is now replaced with t, and like we said earlier, our vertical intercept is -4 meters per second. That concludes